this lecture is over what's known as entropy. So before we get to that, let's talk a little bit about spontaneous versus non-spontaneous. Versus a non-spontaneous process. So just a couple of examples to illustrate the process. So if you have a ball on the hill, for example, and if you position the ball right there and release the ball, then it's going to spontaneously roll down the hill, right? Or if you had a couple of chambers set up, separated by a wall, and there were gas molecules in them, and if this one was hot and this one was cold, then what's going to happen over time? So then over time, well, so at the molecular level, first of all, what's going to be the difference between the molecules? So these would be fast moving gas molecules, and these would be slow moving gas molecules. So over time, what's going to happen? So if you set this up and then came back a few hours or a day or two later, what would you expect to find? So these are moving, these are moving. So then they would be moving at the same speed, right? Because so basically what's happened is heat has there's been a flow of heat from one chamber to the other, and that was a spontaneous process. So you can make a non-spontaneous process work. But you can make the ball go up the hill, but how would you have to? What had to be done to make the ball go up the hill is you would have to expend energy. Okay, so entropy then. So what is entropy? It's a measure of the order of a system, or a measure of how organized the energy is in a system. So a couple more examples. So if you have a hot cup of coffee, on a table, in this case the energy is organized, it's all in that hot cup of coffee, and then over time, what would you expect to happen if you came back a little while later? No longer hot. Now of course you have now a cold of coffee. So where did the energy go? Well, the energy went to the surroundings. The energy went to the air, to tabletop. Maybe the tabletop's a little bit warmer. The air went to the air molecules around the coffee cup. So in this case, then the energy is dispersed. Right, so in terms of entropy, this would be low entropy, and this would be high entropy. So low entropy is when the energy is organized, and high entropy is when the energy is more dispersed. Or if we had an example like this, so a couple of chambers set up with a valve here, and so there's air molecules in here. And then you open the valve. Then what's going to happen is, of course, the air molecules would eventually fill both chambers. So in which case is the energy more organized? It will be here. And here the energy is more dispersed. So this will be of low entropy, and this will be high entropy. Okay, so if the process is spontaneous, entropy increases in a spontaneous process. It goes from more order to more disorder. Okay, so just one more example, chemical example. So if we had a block of ice, at the molecular level, if you remember from Chem 1, what this looks like is water molecules would be all hydrogen bonded to each other, and then if this melts, of course the water molecules are still hydrogen bonded to each other, but what's the difference is that here the H2O molecules are in fixed positions, they only vibrate. And whereas here in the liquid, the H2O molecules can move. So which one's of higher entropy? Well, this would be of higher entropy, so it's more disordered. So the entropy of a block of ice is 41 joules per Kelvin, whereas for liquid water at the same temperature, so both of these at 0 degrees Celsius, the entropy is 63 joules per Kelvin. So then of course you can calculate change in entropy. For the melting of ice at the same temperature is 21 or 22 joules per Kelvin. So this is the second law of thermodynamics. The total entropy of a system and surroundings always increases in a spontaneous process. Okay, so you can predict the sign of entropy for chemical reactions, sometimes just by inspection. So if we take a few examples, so N2O4 gas goes to 2NO2 gas. So as delta is change in entropy greater than 0 or less than 0. So you can figure this out by looking at the order of the system, so which is more ordered and which is more disordered. So here all of the atoms are in one molecule, and here atoms are in two molecules. So that's more disorder. Right, so this would be, so the right side would be of higher entropy and the left side would be of lower entropy, so in this case delta S would be greater than 0. So if you take a molecule and break it apart into smaller pieces, that's going to increase the entropy, and that's going to be a positive entropy change. So if we take a few more examples, so CS2 liquid goes to CS2 gas, 2H mercury liquid plus oxygen gas goes to 2HGO solid, 2Na2O2 solid, okay, and one more. Let's say CO gas plus H2O gas. Okay, so if we take these four, so here in the first one, liquid goes to a gas, and so which is more disordered? Right, a gas would be more disordered because once the molecule's in the gas phase, they can move all over the place. So this would be a positive entropy change would be greater than 0. So in general then, if you go from solid, okay, so then also going from a solid to a liquid or a liquid to a gas, if you're doing a phase change, so solid to liquid, liquid to gas, or solid to gas, sorry, then all of those would be a positive entropy change. Okay, so in this second example, so you have mercury liquid and oxygen gas, so two molecules combining to make, so two separate molecules combining to make one molecule, then that's going to be an entropy change that's less than 0. Because here you have two separate molecules, and now, well, actually you have three separate molecules, right? You got two of these and one of these, and you only make two of these. So you go from more disorder to more order, so that's going to be a negative entropy. Okay, so this third example, so let's see. We have a solid and a liquid, and sorry, this is aqueous, and this is a gas. And we're going from 4 molecules where they're solids and liquids to 5 molecules, and one of them is a gas, so that's going to be going to more disorder, so that's positive entropy. And for the fourth example, so we have 2 molecules and they're both gases, and we're going to 2 molecules and they're both gases, so this delta S should be around no change in entropy. Okay, so for a spontaneous process, So if we relate entropy to heat for a spontaneous process, the change in entropy is greater than delta H over T. We're not going to drive that equation, we'll just have to know how to use this equation. So then if we rearrange that equation, so delta H over T minus delta S is less than 0 for a spontaneous process. And if we arrange that equation, multiply everything by T, delta H minus T delta S is less than 0 for a spontaneous process. So basically, if can calculate delta H and delta S, and you know the temperature, then you know if a reaction is spontaneous or not. Okay, so so we looked at before how you can calculate delta H for a reaction. You can do something similar for delta S. So delta S values are known for many compounds. They're placed in tables. And so if you want to calculate the entropy change in a reaction, then similar to how you do it for delta H, it's a summation of the entropy of the products minus the summation of the entropy for the reactants. So if we just take one example, so let's calculate delta S for this reaction. So glucose, so that's solid, goes to 2C2H5OH, so ethanol, plus 2CO2, gas. So what's delta S for this reaction? So you just look in Appendix C, get the S entropy values for these compounds. So for glucose solid, it's 212.1 joules per Kelvin. For ethanol, it's 160.7 joules per mole Kelvin. And for CO2, it's 213.7 joules per mole Kelvin. So the change in entropy for this reaction, so sum the products. And don't forget to multiply by each of these numbers by the molar coefficient. So 2 times 160.7 plus 2 times 213.7 minus 212.1. So the entropy change for this reaction is 536.7 joules per Kelvin. So that's a positive entropy, so delta S is greater than 0. And you might expect that from this reaction, right? Because you have a solid goes to 2 liquids and 2 gas molecules. So one molecule basically gets split up into 4 different molecules, and 2 of those molecules are gases and 2 are liquids, which are both of higher entropy than solids, so delta S should be positive for that reaction. Okay, and we'll stop there.